A legal professional needs an immediate historical fact, so they query an AI model with an exact question. Who were the first 3 female judges of the Abu Dhabi Commercial Court? The model replies with absolute confidence, naming Aisha al-Suwaidi, Layla al-Hamadi, and Reem Khalifa, stating they were appointed under Federal Law No. 17 of 2012. Every detail in that response is a complete fabrication. Those judges do not exist, and the cited law has no connection to the commercial court. This output perfectly mimics the exact formatting, tone, and syntax of legitimate legal expertise, making it uniquely dangerous for enterprise professionals. Users commonly assume the system is searching a vast archive to retrieve this information. In reality, large language models possess no database, no internal rulebook, no active memory, and no factual awareness. The system is an autoregressive inference engine. It is a mathematical model that predicts the next element in a sequence based entirely on the elements that came before it, using statistical weights rather than factual truth. To rely on these tools in high-stakes environments, professionals must analyze the mathematical mechanics driving this synthetic overconfidence. We have to zoom in to the smallest unit of computation, the token. A token is a fragment of a word, like breaking unbelievable into subword components, illustrating that the AI processes text mechanically, not conceptually. The model operates on an autoregressive loop. It writes text strictly one token at a time, calculating its next step by analyzing the entire chain of preceding tokens. This matrix assigns raw mathematical scores to thousands of potential next tokens. The system selects the token with the highest statistical likelihood. In our Abu Dhabi example, plausible-sounding Arabic names spiked in probability purely because they statistically co-occurred with surrounding legal vocabulary during training. This generates a token dependency chain, a sequence where early words mathematically restrict the possible choices for all subsequent words. The fatal flaw of this chain is its permanence. Once the model commits to a narrative structure, it cannot pause, run a self-correction, or signal epistemic doubt. It favors structural continuity and momentum. It will seamlessly build an entire argument on top of a factual premise that is entirely flawed. Hallucinations represent the system successfully fulfilling a statistical pattern despite lacking any underlying epistemic grounding. Moving past how the text is generated, we have to examine the style of the output and compare its structural rhythm to authentic human writing. Natural language processing relies on a metric called perplexity. Perplexity measures the predictability of a text stream, where a low score indicates the model has extremely high confidence in what word comes next. Large language models inherently optimize for low perplexity. They default to safe, high-frequency syntax and cautious hedging structures to simulate a professional tone. We also measure burstiness. Burstiness calculates the variation in sentence length and structural complexity throughout a passage. Authentic human writing exhibits high burstiness. It is irregular and erratic. AI writing maintains unnaturally consistent cadences. This diagnostic overlay maps our fake Abu Dhabi legal text, revealing unnaturally low perplexity and burstiness scores. The output is mathematically too polished to be human. The exact traits that make this text sound flawless are the structural artifacts used by AI detection systems. Those algorithms exploit that lack of variance to mathematically flag the text as synthetic.
Fluency must never be mistaken for accuracy. The professional polish of a language model is a statistical byproduct, not a marker of truth. A common misconception is that models retrieve static answers. In reality, the output is non-deterministic, meaning identical prompts will naturally yield different results. This variation occurs because the model doesn't automatically pick the single most likely token at every step. It samples from a distribution pool to introduce natural variation. We control this randomness with temperature. Temperature is a mathematical scalar applied to the output calculations to control the entropy, or variability, of token selection. This bell curve shows token probabilities. Under a high temperature, the distribution flattens, increasing variance and raising hallucination risk by permitting low probability tokens. Under a low temperature, the distribution sharpens into a spike, forcing the model to pick only the most probable conservative tokens. A secondary filter is top P, or nucleus sampling.
Top P dynamically restricts the model's choices to only the smallest group of tokens whose combined probability meets a specific threshold, cutting out the noise. High entropy sampling is highly effective for creative ideation, but for legal analysis or technical data retrieval, it guarantees failure. If a low temperature had been forced on the Abu Dhabi prompt, the model would have been stripped of the statistical leeway required to invent those fake names in legal citations. Unpredictability in AI is an architectural feature that must be actively managed. Uncalibrated sampling in enterprise use guarantees synthetic overconfidence. Professionals frequently approach prompting with vague, monolithic instructions, communicating with the software as if delegating a task to a human assistant. Monolithic prompts fail because they saturate the context window. This triggers instruction decay, a phenomenon where the model forgets earlier parameters as the memory space fills up. We have to evaluate the generative AI engine against its three actual limiting factors: the pre-training data, the keywords supplied, and the token capacity. In this pipeline, the user input must be tokenized, processed for pattern matching against the training data, and decoded back through NLP to generate an output. The practical solution is lexical anchoring. Lexical anchoring is the deliberate use of dense, domain-specific terminology to heavily bias the model's internal attention map. These keywords act as weighted nodes, pulling the probability distribution towards specific latent document clusters, successfully mimicking the vocabulary of actual regulatory textbooks. Look at the transformation from the weak Abu Dhabi prompt to a rigorous anchored prompt. These explicit constraints physically restrict the internal decision space during generation, stripping the model's capacity to venture into low-probability guesses. Coupling this with sequential prompting, breaking complex tasks into small, verifiable steps, prevents the model from guessing and strictly preserves the token budget. Explicitly requesting the model to cite specific sources or dates is a trap. Because it lacks a verification database, demanding citations actively forces it to hallucinate references. The reality of prompt engineering is that you cannot program the model with rules. You can only trigger dynamic simulations based on its statistical exposure. Genuine expertise requires navigating the reality of a probabilistic engine, one where precision is mathematically forced, not politely requested.